My name is Stephen Nelson, and I'll be presenting CountNet3D, a 3D computer vision approach to infer counts of occluded objects. This paper was led by Porter Jenkins from Brigham Young University and was a joint work with the others listed here. We've studied the problem of visual object counting. Object counting is an important and challenging problem with a large impact on organizations. Industries like retail and agriculture rely on counting methods for inventory tracking and estimating crop yields. These tasks are time-consuming and error-prone. A system that could automate these tasks could be a powerful tool. However, obstacles like occlusion, particularly when objects are densely spaced in a scene, can be challenging. Two common strategies for object counting are regression-based methods that predict object counts directly from the scene and detection methods that classify and localize objects. However, research on regression methods is limited to two-dimensional scenes, and detection methods struggle when applied to problems like ours, where objects are densely spaced and highly occluded. A recent seminal detection method applies a frustum proposal step, where a mature 2D detector is used to create a pyramid of view called a frustum. Points from the scene point cloud are filtered into the frustum proposal, and this is fed into the network. By creating this frustum subcloud, the search space is reduced, and the network can focus on extracting features from a much smaller area. However, this method was designed for constructing a frustum containing one visible object. To solve these limitations, we propose the following. CountNet3D, a novel 3D regression network that processes RGB images and LiDAR point clouds and outputs fine-grained object count estimates. We introduce point beam proposals that use the shape of the 2D bounding box to facilitate very fine-grained count estimates by reducing the search space to local neighborhoods around known objects. We use a PointNet backbone to predict fine-grained object counts and show that regression-based 3D counting methods outperform state-of-the-art detection methods. Lastly, we offer an open source, large-scale dataset of simulated LiDAR scenes, which we make publicly available. The CountNet3D architecture takes in a 2D image and 3D point cloud as input. We apply a 2D object detector to the image, project those predictions into 3D space in the point cloud. These detections are used to create what we call a point beam, which reduces the search space to a rectangular prism containing the points in a local neighborhood around known objects. We then pass a batch of these beams into a PointNet network to generate a geometric embedding. We then reduce the number of classes by mapping each fine-grained class to one of a much smaller number of geometric classes and concatenate a one-hot encoding of that class to the geometric embedding. This point representation is used to make a count prediction for each beam. In order to construct each point beam, we extend the 2D detection along the normal vector in 3D space, then map each point to its corresponding point beam and discard points that do not fall in a beam. Each beam is associated with one of 3,000 plus fine-grained classes, and each fine-grained class is associated with a corresponding geometric class. We run our experiments on two data sets that we have collected. The first is a synthetic data set we created with around 24,000 scenes, 4,074 fine-grained classes, and 5 geometric classes. Results on this dataset show that, in general, regression methods outperformed detection methods, and our regression method performed the best. The other dataset is a real-world dataset collected using the camera and LiDAR sensor from an iPhone. This dataset has around 7,000 scenes, 359 fine-grained classes, and 21 geometric classes. Qualitative results on these two scenes and average results over the test set show that among regression methods, CountNet3D outperforms others and shows strong performance, specifically in this domain.